Hi students. Today I wanted to cover the topic of Lenz's law, eddy currents, back EMF and electromagnetic induction. You can see that I've linked them all together. There have been some questions from some of you in regards to this topic. Maybe it's just because we were doing our depth study at the time when we were going through this material that you didn't concentrate on it so much. And I put this together this morning and I just wanted to quickly explain it. If you're after some more detail, and this is somewhat general information in here, then have a look at the textbook. I've made some references to the textbook in these notes here, but that's a good source to get into the information a little bit more deeply if you need to. All right, let's make a start. All of these concepts are linked, yes, and hopefully this document here will help you put it together that little bit more. All right, so let's start with electromagnetic induction. Well, it all started with Michael Faraday, would have been 1800s or so, who discovered that a voltage can be generated by moving a coil through a magnetic field. So if you have a wire, it doesn't even need to be a coil, but a wire, and you push it through a field so that it's feeling a change, then a current will be induced in that wire. And that's the gist of it. So changing magnetic field relative to a wire. There is a diagram that sort of explains it, and you will have seen this one here in class, where we've got a magnet, and you can see the north and the south on it there to the right, is moving towards a coil. And the coil here, well, we've discussed this before, produces a north up that end to try and repel or oppose, and we're going to talk about this in a minute when we come to Lenz's law, and produces a current. This is the effect that induces an EMF and creates electricity, and that's what Faraday discovered. Another example I've got on my laptop here, you should be able to see this animation. I'm just going to start the animation. Let me get my mouse over here on the left-hand side. And you can see that this wire is connected to a voltmeter and they're passing it through the magnetic field, and it causes the electrons, which are those dots, to move. And as it moves into, I guess the dots move in one direction, the electrons. As it moves out of that, the dots move in the opposite direction. It's just going to do it once more. So as simple as a wire moving through a magnetic field to create a flow of current. And that's what Faraday found. Another way of saying that is if we change the amount of flux passing through a coil. So we talk about magnetic field strength as being the flux, and if that changes going through a coil, a current will be created in the coil, and we'll have a look and see how that is generated in a minute. So it can be a straight wire or it can be a coil. There is an equation that is related to this, and you should be familiar with this equation already. E, that funny symbol on the left-hand side, stands for electromotive force. And that equals the negative of the change of flux. So that phi symbol on the top of the fraction there is flux over change in time. And underneath it says that as well. Let me turn off the YouTube video. It's just going in the background. There we go, it's off. And then what we have down below, and phi, just in terms of describing what phi is the multiplication of the magnetic field strength, B, by the area of the coil. And you can see that little symbol right next to the B, which means perpendicular. The maximum effect is when the magnetic field is perpendicular to the area. And so you've got BA cos theta there as well on the right-hand side. And I've tried to depict a diagram here of a coil turning in a magnetic field. And I've got written there, rotating a coil in a magnetic field creates an EMF. So here is just a coil. There's no voltmeter or ammeter or anything in there, but the coil area itself has more or less flux going through it as it turns. And I'm hoping this diagram helps explain, like at the moment there are 4 magnetic field lines going through the coil. If it was flat, there'd be no magnetic field lines going through the coil, and so you have this change. That change would be the change in flux over time. So it's a rate of change of flux in the coil. What else do I have? Actually, on my computer, let me flick to a different screen. We have a couple of different animations. Let me go to this one first. This one's on FET. You can find it on FET, play with it yourself. I have a magnet here that I can move, and this is a little bit like the example that I showed at the beginning. Move the north towards the coil, and you can see the light on the left-hand side here glow, and the galvanometer moves in one direction or the other direction as we do that. Okay. So the magnetic field from the magnet is affecting the coil, and as such, the coil itself generates an electric current to oppose that motion. Again, we're going to be talking about that in terms of Lenz's law shortly. Okay, back to the sheet. Here, in the next column that I've got, we can use the reverse of the right-hand rule. So this is about predicting the direction of the current. We can use the reverse of the right-hand rule, and the right-hand rule is the one that we normally apply to a motor. Everything that we're going to be talking about here in terms of Lenz's law and eddy currents and back EMF is really about inducing current, which is the opposite of a motor. A motor, you put the electricity in to get the kinetic energy out. But with all of this, we're putting the kinetic energy in to get electricity out. And so for this coil here, and I'm going to use my pen, this coil here is a simple coil. There's no electricity going in. We're not deliberately putting electricity or current through it. We're forcing it through kinetic energy, a rotation. So we're applying kinetic energy, and that will induce a current in the coil. So we use the reverse of the right-hand rule because it's the reverse of a motor to predict the direction of the flow of conventional current. In the above diagram, the current would flow clockwise in the coil. So the current would flow in this direction. Please practice using the reverse of the right-hand rule to be able to predict that. It could well be a question in your HSC paper. Okay, moving down, this graph shows the production of EMF. So this graph here you can see is sinusoidal, and that's really because we've got a rotating coil, and most things rotating will have a sine or a cosine function. The graph shows the production of EMF through one rotation from its starting position. So if it starts in this position here, there's obviously no flux going through it. But what we're talking about is a change over time. As soon as it starts to move, it will be producing electricity because the change in flux will occur, or it'll experience a change in flux, the amount of magnetic field lines going through the coil. Because it's currently at zero, any change is a huge change. Any change from zero is large. And so what we find here, this is the starting position here. You can see that it is a large value. It's not zero, the EMF. It's at a large value. You'll also notice that it's in the negative. And that's because back here in the equation, we have a negative symbol in there. Okay, so the EMF will be the opposite to a change in flux. So a large change in flux means that there will be a large negative electromotive force, and that's what we've got here, a large negative. And then it just goes through the cycle of 180 degrees. At the 90-degree mark, what we have is the coil being upright, and here we've got it lying down flat. We would have the coil upright. We would have maximum flux going through there. But at maximum flux at upright, if it moves from upright to slightly not upright, you'll actually find that there's very little change in the area or the flux through the area. And if there's very little change, that's why we have a 0 point here. Okay. I'll leave that for you to think through. If you have any questions, have a look at the textbook. It describes it in more detail. But you should be able to follow the fact that EMF is produced in a sinusoidal way, or negative cosine in this particular case, because it's rotating. Okay, coming down here, we've got the negative symbol in the equation. The minus here is the basis for Lenz's law of opposition. All right, so I'm going to move on to Lenz's law in a minute. Everything that we've covered in this section so far has been really about electromagnetic induction. And so I want to use this as a segue, I guess, into Lenz's law. That negative means that we're really opposing the motion. Okay, so let's head up to Lenz's law. An induced EMF, and this is Lenz's law, you'll find this written word for word like this in the textbook. That's where I got this from. An induced EMF always gives rise to a current whose magnetic field will oppose the original change in flux. Okay, that whole opposition. And there's this picture again. We can see that the north going in means that there will be a north created in the coil to oppose, because you know that norths repel each other. So the two like poles repel each other. And the only way that you can get north there is that it must have created a current to be able to make that north there. And our right hand, I've written just down here, we have a right hand finger curl rule. Maybe I'll stick my hand in here and describe how that works to determine which direction the current is going to be flowing. Okay, I'll read this first. The approach of the north end of the magnet will cause a magnetic field to be created at the right side of the coil. The galvanometer will show a current to the left to support the north pole in the coil. The right-hand grip rule is handy to work this out. All right, let me use my hand. Here's my hand. Maybe I need to back a little. My fingers go in the direction of the coil, and you can see the coil going over and over. So I'm going to put my fingers in the same direction. So my fingers over. However, my thumb has to go in the direction of the north. So I'm going to point my thumb back in the other direction because the north in the picture is on the right-hand side. I'm going to put my thumb, this isn't working very well, is it, in that direction. My fingers are actually curling over the top. Do you notice that? My fingers curl over the top when I do that, when I point my thumb in the direction of the north, which really means that if my fingers are coming over the top, it means the current will be coming over the top. Current coming over the top. When it does so, it then means that this galvanometer will be pushed to the left. Fingers over the top means the current will be going in that direction because I've got my thumb pointed to this north. Okay, hope that helps. Anyway, practice it, see if it works. I've got a second example for Lenz's law. So this Lenz's law is about opposition to create a current. Down here, you'll remember the experiment we did of putting a magnet down a copper pipe. If we drop the magnet down, the copper coil, and I'll read this, I guess. When a magnet is dropped through a copper tube, the tube creates a current and magnetic field to oppose the relative motion. There is no circuit, so eddy currents are created in the tube. We're going to be talking about eddy currents in a minute. You'll remember that when we drop the magnet down here, the magnet drops rather slowly. Okay, the relative motion of this magnetic field against not a current carrying wire, but metal nonetheless, means that the metal will produce a current to oppose the motion. It will want to slow it down. And that's what happens here. Rather than there actually being a circuit here, there are currents that are set up within the sides of the copper tube to do that opposition. So here's another example of opposing. This is Lenz's law used to describe why a magnet drops through slowly, because it's opposing the motion or the relative change of magnetic field. I do have an example 3 over here, and that's in induction motors. Many of you haven't spent much time in learning about induction motors. This is the use of Lenz's law, but in a different way. So this is supposed to be a description of a motor. Here I've got a center armature, although this armature doesn't have coils in it. It's a block of aluminium. Yes, it is designed in a certain way to be effective, but it's basically a block of aluminium. And around the edges, we've got electromagnets. Okay, if I cause this electromagnet to be a north, all right, and then I switch it off and make this one the north, and then switch it off and make that one the north, and so I'm progressively moving my north around in a circle. The center aluminium section here, which is made of metal, a conductive metal, it's not attracted to the magnetic field because it's aluminium. However, the aluminium here will say, I don't want that change. I don't want the north moving around in a clockwise fashion. I want to oppose that motion, which means the opposition of a change means to stay the same. So this section of the armature here, which is up against the north, will want to move around to be near the north when it appears here, and then move around to the north when it appears here. And all of a sudden, we have an armature that spins. And this is an induction motor in its very basic form. It is a spinning aluminium section, armature, that moves with a magnetic field around the outside, or in the case of the motor. Most of our motors that we have are like this in our regular life. I have an example, and I'm just going to show you this here. This is an example of an induction motor. I can spin this, and you'll notice that this section down here that's spinning is aluminium. There's no wire. You can't see any wire there. All it is an aluminium blob, chunk, that sits within this frame. And this frame here will have a magnetic field applied to it that changes. So this coil here is designed to change the magnetic field in this outer section, switching it on and off and making it rotate, such that the motor here will want to follow that change in magnetic field. So here's a very basic, I guess, model of an induction motor. Okay, again, Lenz's law to oppose any change in flux, change in magnetic field. It will want to oppose that change. All right. Okay, so let's keep moving. Eddy currents. So we're now moving on to eddy currents. Eddy currents, most of the time when we talk about them, are in relation to transformers. The AC power in a transformer creates a changing magnetic field in the primary coil. So here's our primary coil. If I have an AC, voltage or whatever and current applied to this coil produces a magnetic field. You know that already, okay? If you provide a magnetic field in this coil, and if it's changing through the nature of the AC power that's going in, the induction coil will be changing. It means that the metal here, the metal structure, the iron core of the transformer, I've only drawn half of it here, will create little currents, and we would call them eddy currents, little currents here, and you can see I've drawn them in red, and they're supposed to be little arrows that are spinning. They will be created in that iron core as the iron core becomes magnetized. Right? The iron core becomes magnetized and it sends its energy over to the secondary side. However, in the meantime, we have these currents created. And because those currents are there and because the iron core has resistance, these little guys are rather vigorous. The AC power here turns on and off, or backwards and forwards, 50 times a second. So these currents will be doing exactly the same. 1/50th a second that direction, 1/50th in a second the other direction. And so they're backwards and forwards really suddenly. And so because of that change and because of the resistance, it means that heat is produced. And heat is a form of energy that then is lost to the system. This transformer is no longer 100% efficient. Okay. And the syllabus does ask, and I wasn't going to cover it here, about how to minimize those eddy currents. If we can make this iron core laminated, it then means that the eddy currents are limited by physical size as to how big they can be, and that then limits the amount of heat produced. By the way, if I go back to, let me bring this in, back to my induction motor, look at the laminations here of the metal. Can you see them? There's got to be 20 of them in there. And that limits eddy currents even in the induction motor. It limits the heat loss. Anyway, hope this is a bit of a reminder. If you read through this, this is really what I was describing. I want to move on. We've done induction motors. Let's move on to the last section, which is back EMF. And you might be even less familiar with back EMF and may not have spent so much time on it. Okay, you have to follow me with me on the thinking of this. It's just a little bit tricky to get your head around the first bit. When a motor spins, let's imagine we've got a motor now. We've got a motor that is spinning. The current is pushed into the coil, so we use current to force the coil to spin. All right, that's the way a motor works. We put voltage and current in to cause the coil to spin. All right, now, Lenz's law, we have created a changing flux in a magnetic field. So now we have a spinning coil in a spinning coil in a magnetic field. We've created one deliberately. And if we go back to here, we've got a coil that we're deliberately spinning in a magnetic field. What happens? Well, we produce electricity. And that's what all of this is about. We induce a current. We're producing electricity. So despite the fact that we have a motor here and our intention is to make it spin, we have an opposing force. And Lenz's law comes into play. Lenz's law wants to oppose this change. When we make a motor, we are working against Lenz's law. All right, what happens is that the EMF, a back EMF, an EMF is created to oppose this motion. The EMF will be in the opposite direction to the driving current. We're pushing current into the system or into the circuit, but we have a back EMF that is pushing back. This back EMF limits the forward spin of the motor. Obviously, it limits the forward current. If we've got current going in and some coming back, it limits the amount of current pushing the motor forwards. Okay. The back EMF is never as big as the forward EMF, and its size is relative to the RPM of the motor. The faster the motor spins, the more back EMF there is. The smaller the RPM, the smaller the back EMF. All right, and I've just put a relationship. It's the last thing on the piece of paper here. Here's the RPM. As the RPM increases, we can see that the back EMF also increases. Okay, I'm hoping that this has given you a bit of a summary of how all of these concepts are linked together. I will send you a scan of this document as well as with this video, so that you've got that to refer to. And I'm hoping that, I guess it explains it a bit more for you and helps you in your revision. All right, the video's gone for a bit over 20 minutes. I think that's long enough. Ask questions if you need to. See you later.